Good morning all. Apologies if I've not got this set of notes to you sooner. I know it's been almost a week since we've met about using Matlab and SimMultibody. What I want to do today is really bring you up to speed with what we were doing, take you through the whole process, and take it so that you can really, have a good look at the software. Apologies, I had WhatsApp open at the same time, so if you could hear that, that's where that was coming from. Right, so let's get into it. If you've not done already, open up Matlab. Obviously, I've already had this loaded. Just as a reminder, as navigating through the videos on YouTube, some will keep reiterating this. I like to reiterate this. I like to be aware. I like to be complete onto what we're doing and why we're actually doing it. Just before Christmas, I was asked to do a bit of market research as to which is the most employable software out there at the present. I actually got some interesting results. From it, I found, 2 seconds. Yeah, I actually found that as far as analysis software goes, just before Christmas on the engineer as a job, what they were actually talking about is they were talking about what softwares are the most employable things to be using. The most employable thing out there at the minute as far as an analysis software goes is actually Matlab. Just before Christmas, 115 jobs were being advertised. 155 jobs were being advertised. For ANSYS, there were 42 jobs, and for COMSOL, there were 10 jobs that were all over the country. For CAD software, there was 452 jobs for SolidWorks. There was 80 jobs for use of CATIA. There was 85 jobs for use with Creo, and there was 1,307 for 2D AutoCAD. So it just kind of puts into perspective. So, moving back to Matlab. As a reminder to everything, this is our direct interface. We have the direct interface to the command window, we have the workspace, and we have the current folder. Current folder we will need to be aware of. This is something that we will just keep reiterating and reiterating. So that's just a quick reminder as to tools and where we're navigating to. What I would recommend first is that we're going to set up a window or folder. So I'm going to go on my desktop, I'm going to right click, I'm going to make a folder, and I'll call this Toqrue Sim. Oh my god, I've just realised how I would spell that. It's a little bit awkward. Right, in my folder, I'm just going to navigate my window. I want my window to always be operating within that folder for this simulation. So first things first, I'm going to click on my browse to folder. I'm going to navigate to my new folder. I'm going to click select folder, and then I'm in an empty workspace. Now, what I can do is any models that I have, I can take them directly, update them, and put them straight into here. Now, I do need to admit to a little mix-up, well, not mix-up, a mistake that I made. But it doesn't affect the learning side of this, but it does affect my ego. So, first things first, I've gone to Blackboard already, and I have downloaded the wheels. So let me just grab my wheels. If you've not done already, get yourself onto Blackboard, download the wheel blocks, and then, well, the wheel step files, and then let's crack on. Let's take a further look. So, if you've not done, unzip the file, and then copy them, place them straight into this folder. So now we've got our target materials, and you'll notice on the desktop instantly it gives an update as to what's happening there. So let's get this show on the road. I'm going to go new, and I'm going to go Simulink model. This now I'm going to show you Simulink. Now, because I've already had this open, it's opened up much quicker for me. So you've got to remember this is an extra bolt of software which until you run it and it initializes, it will always be quite slow. Once it's run, it'll be quick, not a problem. As a quick reminder, this is our Simulink, I think you could call it the startup, similar to like if you're in a CAD system where it says do you want to do a drawing, a part or an assembly or any other particular configuration that you're interested in. It'll give you your recent things that you were working on. So for example here I've got skull. This is where I was looking at the type 1 lever system for the human head and what type of force it needs to balance out. I was looking to verify some physical test data that people had done, and yeah, it's, if you're not interested, it's very dull. To the right we've got examples, and don't forget on our examples, if you are in particular interested in looking at electric motors, if you're interested to look at servos, human signals, or you're interested in actuating for different principles, so aerospace, anything like that, here is a good place to start. Gives you everything you really need to see stuff in action. I've built a lot of my stuff thinking, how does that block work? They give you an example and you can explore it. Makes it really useful. Anyway, so for my Simulink block, I'm going to go here and go create model. What we're essentially doing is we're working through the nodes that are up there. But what I want to do is build it in Simulink and then test against what I've got. As we're going through, I'll point out my mistake and what had happened. I intend to fix it, but I like to just point it out so you guys are aware as to where the hell them values came from. Because that's what happened to me. I've gone through and gone, that don't make sense. Then gone all the way back and gone, oh, I forgot to do something. So it's purely my mistake, but it doesn't affect the learning for this. So let's go into the library browser. Then our library browser, this is everything we're going to need. They reckon with this you can pretty much do almost next to anything with it. I don't think there's any blocks that we don't have. So I'm told industry copy, something like this would be between, I think it's 100 and, somebody told me yesterday it was £155,000. I don't know how true that is, but when you consider it, each one of these tool blocks tends to be sold around 500 to 700 quid. It can be quite steep, but it's because it's so powerful, because it's so useful. And nowadays what a lot of companies are starting to do is go, well, if we've got this superpower at our fingertips, why are we even using FEA models when we can actually formulate our own methodologies for solving? And what's happening is, I'm not saying that things like ANSYS are completely irrelevant, because they're not, far from it. But these are being challenged by these things, and this is what makes Matlab that little bit more employable. Right. So let's crack on to what I like. Now for me, I love this piece. What we're going to do first is we need to set up a ground. Now, I should call it an origin. We need to give a point of reference for us to begin from. So first things first, let's go to Simulink. Simscape, sorry, we're in Simulink. My God, I don't know how fast are my shoelaces. Right, first thing we need to do, we need to establish a zero marker, so an origin. We need to establish a solver configuration. We need to establish a world frame, in essence, where we will begin from. So, first things first. And also, we need gravity. So, any budding physicists out there, and I know there will be some of you, this solver configuration allows us to use all of Matlab's ODEs dependent on your time settings. At the minute, we are set to what's called predictor correctors, but you can correct this. As we go through, we're going to do this. We're going to look at the changes. We're going to look at mass spring dampers under different states, and we're going to look at verification of these mass spring dampers, what it gives us, just because it's healthy to go through that and take a look at it. Online, I've done some mass spring dampers there. I just want you to really get clear about the functionality of how these things work. Okay, so I've dragged and dropped a solver configuration. I'm going to press spacebar. It just brings it up to a zoom to fit. I'll double click into that. This now gives me consistency tolerance, or what my plus and minus would be relative to each time iterative step. My how tight this simulation will be. This tends to be very robust. I don't like to change this at all, ever. I personally prefer to try and edit the configurations around, but I mean, sometimes obviously you must change this. So I think there's going to be a couple of times we are going to hit this and we are going to have to change it, but let's just take it steady away. So I'm just going to zoom out, put that one there. So next thing I need is I need to get my ground, and I need something to give me what will be my equivalent gravity. Don't forget, we can change gravity to different components. We can alter its state in different times during the running simulation. We can do all sorts with it, and it will give us some incredible results. So first things first, I'm going to go to Multibody, and I'm going to go to Utilities. Let's bring in a mechanism configuration. And it sounds very mechanical, does that? I mean, it's a sodding arm, for God's sake. It's a robotic arm. First things first, let's take a look inside. We get onto inside. We've got uniform gravity, constant, time variant, or none. We can put different things in there. We can even change this gravity here to a variable. So as it's running through a different time state, once it hits a particular time, that gravity can update. It can change relative to an equation, for example, that's going on. So if you're entering from the stratosphere as Mars and you're coming into Mars, the gradual changes and the impact it has on the system, you can actually put that in there. So what I'm going to do is, because this is an XYZ component mechanism, I want to move my gravity to being the Y component. This is purely because everything in sim mechanics is defaulted to Z. The reason it does that is because when you drag something in, you can always know that its configuration is always going to be at Z. If you're not happy with that, which is fine, what you know is that you've got to make sure that your system is reliant to wherever it sits. So in other words, you move it as long as you're aware of that's what's going on. So what I'm going to do is I'm moving my gravity from Z and I'm putting it in Y. I'm going to apply. Now what we've got is it compliant to Y, so click OK. Next thing, let's go on to body elements. Oh, sorry, not body elements. We're going to go on frames and transforms. I need a ground position, a particular starting point. Now in frames and transforms, it gives me a lot of points for me to be able to do different things. Rigid transform will allow me to shift axes for something to move in a particular way. When we hit the reciprocating mass, this one is where we're going to be at. But for this, I'm going to drag in my world frame. So I'm going to control that. Control R. Come on, click again. Control R, Control R. Right. So now what we've got, if I bring this to here and this to here, what we've got is, I suppose you could call it, we've set up our virtual world. I mean, I think in session I actually did quote it as being setting up a virtual world. It kind of is. It gives us them gravity bit performances. So when we drop things in there, we'll get an effect based on the components that we've chosen. As in my case, for example, I chose Y. But don't forget, there is no particular ground for this to have contact with. This will just drop into oblivion at the moment, because in essence we're in control of that world. Right. Two seconds. Okay, right, so moving on swiftly. Now the way that this system operates is when you're operating from a ground, it wants to know what the first level of performance would be. If it's a spring damper, it will know that there'll be linearity of that spring because it's going to be moving a particular component. The mass plays a separate role. What we're describing here is a joint behavior, nothing more. And then we attach the body to that behavior, and then it will be relative to that response. So you'll get a feedback loop from there. Right, so what I'm going to do is go to body and elements. I'm going to, within here, you're going to find a few different changes depending on the system that you're running at. Now, I'm going to use from solid, file from solid. Now, This is purely because I've been investigating this. It turns out that there used to be one called SimMultibody, and the import process, there was some sort of inconsistency on that import process. It gave a 0.1 of a moment of inertia difference. I'm still not 100% clear how this has occurred, but when I use file from Solid, it does give me something that correlates perfectly to the CAD model better, which is interesting. Not 100% sure why yet, but rest assured I am searching this one down because it's an interesting one for me, a very, very interesting one. Anyway, so I'm going to drag and drop a file Solid, and the other thing that we need is that joint, that behavior we talked about. So let's have a look. Joints. Now, because we're examining torque under present state, I'm going to drag and drop a revolute. The revolute is this. Now, please don't be misled by the drawing that you see. The drawing that you see just simply shows what could be just a simple rotational joint. Now, the model that you're building onto this isn't that model, if you will. What it's just trying to show you is how that joint behaves, to give you almost a picture so you're aware of what that's doing. So just for your notes, because you do need to save this at the end, I'm going to change this to wheel rotation. Wheel rotation. Right, so that is just describing, if you will, the bearing that is the interface between the axle that where the wheel is sitting on and the wheel itself. It's the best way to describe it. So we have the base and we have the follower. So the base describes its initial point where it's sitting at, its housing, or the back, if you will. The follower refers to, as that's been initialized, what's actually following within that state. In our case, it's the wheel. So what I'm going to do is I'm going to rotate this, Control R, Control R, Control R, and I'm going to snap that up. If that happens, it just means you made a mistake. So I'm going to do it again. That's better. So now we've got that connection. Now what we're going to do is I'm just going to rotate this. I want this to be above. Now I would prefer to have two wheels. We've got two wheels to test, don't forget. So I'll go wheel 1. And I'm going to right click and drag. Wheel 2. Now, wheel 2 for the minute, let's put that in the background. Now you can use a comment out function. It is rocking. If you don't know about it and you've ended up with that, it can be frustrating. Totally get that. But for this, it's rocking. So, right click, comment out. That now is ignored. I can deal with that afterwards. My first priority is wheel 1. So let's get these connected. Right, so next thing is, let's get into here. When you double click, I tell you, I nearly made a mistake myself then. When you double click in, you've got an empty file name, you've got from file, you can go custom, oh yeah, look at that, you can go custom to millimeters. Oh, look at that, I quite like that. That's very nice. So what I'm going to do is go file. Once I click onto file, you'll notice you've got your browse. So let's browse. Now, because I was operating from my file from the start, what it allows me to do is select the step file straight away. When it comes in, Matlab says, right, there's been a change that's happened, let's see an update. Boom, F5, there you go. So you'll notice from the notes, that is our new folder type. So I'm just going to make that bigger. Now there's a few things about this. They have what's called the frame connectors. So if I click up here on what looks to be the what will be a datum, if you will, it says toggle visibility of frames. So if I toggle that on, what you can see there is an X, Y, Z. So X is red, Y is green, and Z is like a I think it's blue. So it gives you an idea of where that z-axis is sitting. This will be dependent as to who modeled this originally. If somebody's modeled this and they've been awkward and they've messed around and they weren't really good at what they were doing, you'll end up with an axis like over here. You will have to reset this. Now, I modeled this to be sure for it to work exactly as we wanted it to, and as we're going through, I'm going to give you some awkward models. I've tried to model them so they're completely out of perspective, just so you get the experience of resetting this. It's a bit of a frustrating thing, but it's just something that is useful to do. Right, so we need an inertia. I've just realised I've not actually opened up the notes yet. So 2 seconds. Let me just pull these notes, wherever they may be. Swear to God, I'm sure I had them here somewhere. There we go. And that's definitely not the one. Happy days. Right, so I'm just going to zoom in. We know we're operating to alloy steel. We know our fundamental equations is what we're going to use. We know the size of the wheels. This was here, by the way, because originally in SolidWorks you needed to define a crank fixture. And yeah, that's a thing of the past right now. Anyway, so now that's me changing them to get them updated. So let me just find the correct ones that you guys have been working to, because I'd like to just go through that process, and I'd like to really spell out where my mistake, where I'd rushed, and the mistake that was caused came from. 2 seconds. 2 seconds. I'm just going on Blackboard. I'm just going to download them now. Three, two, one. Phenomenal. Right. So let's go back to it again. This is more like it. Right. Again, same notes, but I've just been correcting them. I've like to work to what you've been given. So we know that the wheel is 65.87 grams. So what I'm going to do is I'm going to come back into here, go into my derived values, and it says here density from file. Interestingly, some CAD systems will allow you to export the density and actually put it in the step file. I've been going through SolidWorks this morning looking at to see if this is a configurational option. Turns out it only is a function in premium, not in student version. So we still have to do this by hand. I say by hand, it's simply a value. So what I'm going to do is go custom mass. It now particularly says what's your weight, so I'm going to go 65.87. We're presently in kilos. I actually want to be in grams. I'm going to update, and we have all of our density, center of moment inertia, and everything that we need. So I'm going to click apply, and now that is my first wheel configuration complete. The next thing is when we go through the notes. We know here that we're going 1356 Newton millimeters of torque being applied. Now this is in a continuous process. Please don't be misunderstood with this. When it comes to continuous torques, if you use a constant value, what it means is a constant increase of a present value. So if I went 1 over time period, it'd go 1, 2, 3, 4, 5, 6, 7. So what we need to do is condense that down. Now we know that we're going to run this over. How long did we say we're going to run it for? I tell you, I should have been more prepared for this. We said that we're going to run this for 8 seconds. In my stop time here, I'm going to change that to 8. Then what I'm going to do is come into my wheel rotation. Now what I'm ready to do is to start setting up stuff that I'm after. So what I know is particular things I will be interested in extracting is acceleration and velocity. Things reminding me of stuff, swear to God. So velocity and acceleration, them two sensings I want. Motion is going to remain automatically computed. However, torque is what we're delivering. So I'm going to go provided by input, click apply, and what you'll see is all new boxes have emerged. I'm just going to move wheel 2 over here because wheel 2 is something that I'm going to play into afterwards. Or you can play into it. So what I'd like to do, I think, is really exhaust wheel 1, and then wheel 2 I can leave open to you. I don't need to go through wheel 2 because the initial process of setting it up is the same thing, same again. The beauty is once that configuration runs, the geometry is irrelevant. We've got our dynamics working. It's so good it must be fattening. Right. So, yeah, if anybody wondering, I am a huge fan of Family Guy. Right, I'm going to go library browser, and what I need now is I need to, now you've got to remember what we're doing is we're operating in a data stream which operates to a matrix. So we're now operating in components. We have X, Y, Z, as we know because we were changing gravity to sit in the Y component. When you're delivering a value in to what they call the power stream, it needs to be put into the correct configuration. Now everything is defaulted to Z. What the rotational behavior will do is say, right, accept a value in. Now what the system needs to do is say, yeah, but if you're feeding in like 10, for example, where's my X and my Y? I need something there. So we have a power stream converter. This allows us to jump from linear values through to matrices representation. Right. So what I'm going to do is go to, now I need a power stream to Simulink converter. Just drag that in. We're actually not going to use it for the minute. And now I'm going to go back again, and I need one of the other ones now. Simulink to power stream converter. Right, now, this, when I was first learning to use this, it was a head doer because it just was a bit of an head doer. Anyway, right, so one good thing to think about is whatever that arrow is, if it's the same as this, it means it's an input. If that arrow is not the same as this, it means it's an output. It's just in case if you're looking, you go, I'm so confused, what the hell is going on? That is what we're looking at. So for this, what I'm going to do first is I'm going to comment that out like we did with the wheel 2, and I'm going to rotate this. This is my input. This is my converter. We've actually not got the value there yet, don't forget. So I'm going to just connect that. Now, we know from the notes or the configuration system, we know that what we need is we need to be operating in Newton millimeters. So in my signal input, I say Newton. Now the beauty is you'll notice beneath it says Newton times M. So it's already showing you how Newton meters is represented in this input box. So you can instantly presume Newton meters is obviously going to be Newton millimeters. So click apply. Now we know that we're in the correct format. If we didn't, it would assume it to be meters per second, so you'd have a wheel spinning like very quick. Right. Now, because of the particular type of input that we need it to be held at a state. We don't need to go up, we don't need to go down, we just want it to be a steady state. So what I'm going to do is go back into here. Now, I've seen other people do different things, but personally I build what they call the signal. So I do a signal builder. This allows me to put in a value and say, right, that's what I'm using. So, right, I'm going to go sinks. Wrong one, awkward. I'm going to go sources. Nailed it. Right, for a good design tool, I mean, we've got ramp. Ramp will just go from a steady state and then jump in an increment. You've got step, you have sine wave, you can do all sorts with it. Now, I'm aware that the mechanical bunch, you'll have done bits of these types of functions before. It's really good, really useful, but apologies, there's people walking past the room every 2 minutes. It's really useful. But for me, the signal builder, I do really like it as a first initial input. If you get very sophisticated and you get real live data acquisition, see the from mat file, you can actually bring in a data stream that way. You can actually read from a spreadsheet directly. You do anything that you want with it. Read from the spreadsheets are phenomenal for Gravity, because what it will do is read a particular time step and actually change things, or if you have a variable damping system, if you have a non-linear response of something, phenomenal. Anyway, let's get back to the actual example. So I'm going to drag and drop a signal builder. So 3, 2, 1. It's like magic. So all I'm going to do is spin that round. Control R. Right. So what I'll do is I'm just going to rename this. Again, when you save this, it'll give you a bit of an instructions to what we were doing. So we're going Torque. I've just renamed it as that so that so even I remember, because I know sometimes I look at it and go, what was I doing? Anyway, so what I've done is slim that down. Now I'm going to double click in. I want to see how the signal is being represented. Ooh, excuse me. Right. This is a classic step response. Classic step response is not too good for what we're after. So what I'm going to do is I'm going to go to a constant signal. I want to add a constant signal because that's what it is. 1356 Newton millimeters of torque. So I'm going to click that. Then it adds me another one, which is like, oh, damn it. Now I've got two signals. This one, I'm going to click onto the graph, going to right click, and I'm going to delete. Click OK. So that now isolates it to one signal. What will happen when I come out, you'll notice it's gone red because it was connected to signal 1. It does not automatically adapt, which some argued is frustrating, but some argue say it's a great idea. Now I think it's a great idea personally, but you may think different. I'm just going to click on the signal bar. Notice at the bottom, see we've got 0 to 10. I'm going to change that to 8. Oh yeah, well I mean the simulation's running for 8 seconds anyway, so it doesn't really matter. But that just means I'd have to change this axis here. But my dominant is the time step that's running. This is the frustrating thing for me that I've always had. These signals will need to be configured manually to correlate with other things if you want it to. Anyway, it doesn't really matter. So let's get in. So we know that value is going to be 1356. 1356. Close that. Now you see there, it's gone red. This is purely because it was signal 1, but I'm now connected to signal 2. So without further ado, if you've not done already, save it, hit run. Now what I did there is we have the datum here. See how these are here? Now we've got a base and we've got a follower, don't forget. So this is describing what the base and the follower are doing. So if I run, you've got the base held still, which is how we designed it. Then you've got the follower spinning around that base. And it just kind of gives you a representation of that. Even though it doesn't physically look like it's moving, it actually is spinning. Which for a simulation like this is vital to know. So what I'll do is close that for the minute. So we know that runs. At the minute, we actually don't have anything useful for us. We've just got that. So I'm going to right click and I'm going to go uncomment. Let's start getting some data. Let's start having some shits and giggles. Okay, so I've double clicked out. It says inherent, and what it will do is take a value and just go, right, whatever's presently there, I'll map it. I'm sure whoever the user is will be able to interpret what's going on. However, if you know what your output's going to be, if you know what your units are going to be, get them in there. It will convert it and give you a nice cracking example. So I'm going to go deg second. Now if you're in class last week, you'll know that I always get these mixed up. Always. So I'm going to connect it up. I'm going to right click, drag one out. I'm going to connect it up to this. Now double click here. I'm because I think this is the configuration that's correct. Basically, I'm attaching to velocity and acceleration. If you remember earlier, we turned it on in the revolute joint. And what will happen if I've got these configurations wrong, it'll go, no, they don't work. So we do just swap them round. Knowing me, it's quite possible. Right, so I'm going to get in there and I'm going to go Simulink. Right, so now what I need is I need something to interpret my results. A scope. Again, you guys from mechanical who've been sat in Akinola's class, you'll know what I'm talking about. So I'm going to go here and I'm going to drag and drop a scope. I'm going to number of outputs 2. And now I'm going to double click in. The layout now will be over the top of each other. I personally like them to be separate. It's just what it is, you know. So where you've got the gear here, I'm going to drop that and go to layout. I've had people who prefer side by side. I prefer top and bottom. But again, that becomes to whatever you prefer. I'm not saying that you have to follow my way. You can go side by side if you wish. I prefer top and bottom. So let's hit run and see if I've done this right. Who'd have knew it? Huh? Who'd have thought it? I actually did that one right. So I'm going to double click in. Now this is what I wanted to do. Anybody who's getting this, it was bugging the living awkwardness out of me as to what was going on and why it was so far all over the place. What this inconsistency was right across the board. What I mean is, I'm just going to bring up the notes. Let's get onto the notes. Now, verification we're looking for is 1242 degree per second squared. 1242 degree per second squared. So what we've got is this. Yeah, if you get this, this almost looks like noise. If you look at the scope itself, it's almost giving you what appears to be noise. Look at the variational changes between it. We're looking at 0.1 in each initial points of change. It is 12. It is within my particular values of calculation. And even if I refer to the actual notes that I showed you, we look here, you can even see SolidWorks is getting the same similar sort of variation. However, what's particularly different between this is taken to even greater accuracy between it. There is a greater point of accuracy, and what the system's done is zoomed into that particular point. But we need to be sure that what I'm calculating is something that's going to give me that 1246.75.53. A great way of being able to do this is actually dropping gravity. Now what I mean is this is an effect that's coming from gravity. So that variational change is coming from gravity. So to prove what I'm actually saying is what I'm going to do is I'm going to copy my gravity here and I'm going to comment that out, and let's just remove gravity completely, and then let's just look at the bare bones system with that torque being applied. I mean, the variational change of gravity is so small, it's unbelievable. But let's run that. And what we get is an accurate result giving us exactly what we were calculating. So that's what's present there. Now, interestingly, this slight variational change of density doesn't seem to appear in the old version of a file solid. It seems to cancel out that noise instantly, which some could argue that's great. Some could argue that feels like you're having vital data being filtered out. I'm not still 100% sure what that difference is, but there is definitely a difference there. You'll have to just bear with me with that one because I'm still learning as to exactly what it is that's caused by that. So now we know that this is our acceleration, we know that this is our velocity. So what I'm going to do is I'm going to name these. I'm going to double click on my line, call this acceleration, double click on here and go velocity, and then run again. And what it should do is name the graphs for me, which again, vital for what you're doing. So based on the calculations, based on my particular velocity, I'm looking at 9973 over the actual velocity period. So you look over here, we're about that. If you are specifically interested in getting the exact data, totally understood, but what I'm going to do is I'll show you how to do that. So let's go on to here. Now this is what I was doing earlier. Let's go to syncs. I'm going to drag and drop a display. This display now is pretty cool. What it'll allow me to do is have two separate ones, tab on and tab on. So if I run it, rather than looking at the initial response, I can see exactly what I'm getting and map it against what I've got. Now with that, I'm really happy with that, because what it's doing is it's now giving me exactly what I'm looking for. So I'm just going to drag this out. Oh, sorry, not going to drag that out. I'm going to get rid of that. I'm going to turn this back on, because any good simulation does really need to have gravity taken into consideration. So I run it again, and look at that. If I run it again, it gives me that particular average, so it actually confirms that yes, we are on the right road. It's always nice to have something going right. So now, what we know is we've got these values. What we can now do is start to look at what happens when we change things. Now, just going to come to my signal builder. So what I'm going to do is, what signal did I run through that? So now we know gravity is doing its job. Let's come in, let's add another signal. Let's do something different. So what I'm going to do now is I'm going to put in a step signal. This is going to be my new signal. I know that my top signal here, I want it to be at the same. So we're going 1356. So let's remain at 1356. Let's run that into position. Then what we got is we've got an overall time period. Now I think I think what we should do is cut this time. So if I click here, there you go. What I think we should do is bring this to a total halt, no more torque going on at 4 seconds. Let's see what what happens to the system. So I'm going to go over to T, drop that to 4, and click enter. Now you see there, it's now bent the signal. I can slowly resist it and slowly turn it off, similar to like braking, if you will. Or if I click on the end point, I can actually bring that in to 4 as well. So it's basically motor running, motor off. So what I'll do is come out of there, and now what you'll see is I've got a second signal. I'm simply just going to move it. So let's run it again. Oh, we've got a decline. This is nice. So what we're getting? Oh, look at that. As you'd imagine, it drops off. Can I actually get... No, let's just get... can I actually see in between here? Have we got any type of resistance there? None at all. Acceleration drops completely. It comes to initial end, and then and we should have a good incline on that. Yes, nice incline on that. So okay, so we've got that going on. So as we'd imagined, we pull it off and it will come to a rest. I think that we're going to add some more stuff to this now. Let's do some more stuff with this. Let's see what else we can make this thing do. What I want to do is, can I put an extra block there? Brilliant. I can't do anything with it. So what I'm going to do then is I'm going to add another frame on it. I'm going to go, I think this time, just for gigs, let's start at 0. So if I start here, I'm going to start it from 0. So my point here starts at 0. Then let's climb to, I mean, what if I put on here? So we're climbing up to 11.23 Newton millimeters over 2 seconds. Okay, so let's do that. So let's go to Y and then go 11 0.32 or 23 even. And then we're going over 2 seconds, so we know that that point needs to be at 2. This point, what type of incline have we got here? We're going to run it again to 4 seconds. So this point needs to be sitting at 4 seconds, but we want it to sit at the same state, 11.23. And then what we'll do is let's just drop it out like we did before. So I'm going to bring this point, set that T to 4, and then repeat the same process here. Let's see what type of an impact it has. Okay, so let's run it again. Now what I'm interested in here, in fact, let's just take a look first. There's a couple of things I'm genuinely interested in now. So, oh, that's the wrong... Because don't forget, I've now put another signal on, because, you know, I'm just being daft with it now. Ah, look at that, 0.3356. Let's have a look what we get. So let's zoom, let's use the zoom button. Look at that! Look at that! Exactly, it's falling to the torque that's been delivered for the acceleration. Agreed. We've got the momentum build here. Now, what I'm interested in, let's drop gravity, because gravity was playing a bit of a sneaky role earlier. Let's see if it has any big impact on our present system. I mean, let's face it, possibly not. Might be even down, not at all. I'm just going to repeat the same process, by the way. I'm going to go 0 gravity from here. I'm going to bring that down. You may realise that I really like this topic. Happy? Yeah, okay then. Click apply. Right, so go OK. Let's run it again. Let's see what we get. And we come back in. Not much. So I mean, we can fairly conclusively say that gravity in this state is not playing much of a role at all. You're getting more of a smooth initial response from acceleration, as you'd imagine, because now that vital component is no longer there. We're assuming that it is under perfect conditions and there is not that resistance to be taken into consideration, which is unrealistic, agreed, but it allows us to look at that different effect. So, I mean, this is not in the notes, but let's go minus 3.7. Go apply. If I remember, 3.7 is Martian gravity. Let's get on to Mars. Initially, the response, I mean, you could almost argue that the initial momentum build has been increased, but I don't see much of an increase there at all. Over the 4 seconds, it builds, the velocity retains its speed, but over that 4 seconds, it doesn't come to rest, obviously, because there's no real resistance there at the moment. It will just spin it up. But that's interesting. That's interesting. Okay. So let's get back to Earth. If I'm just going to bring back in my mechanism configuration, and then let's now look at what happens if I introduce a damping coefficient. Now, these damping coefficients can be useful if you're wanting to give a representation of a coefficient of friction or anything like that. Really, I'd start off with a value. Once I got happy with this thing running, then I'd look into coding this and reading this directly from a variable. So I'm going to go 0. A good value to start with, 0.001. It's a very mediocre bearing interface, but if I run it again, type of a response that we get. That drops it drastically. Acceleration goes through the floor. Now, I'm sure a few of you were wondering as to right, sorry I lost my trace. I lost my track. I'm sat in the lab in the IC, and it just turns out today tends to be super busy. So, in a nutshell of everything that we've done, we've established the wheel, we've looked at different signal settings, we've looked at the different impact on it, we've established the mass, we've established everything, and it runs smooth. The system now is kind of like changing the wheel on a car. So I could simply take this wheel, snap it straight over the top, and everything works just as well. I'm going to let you do the second wheel, just because it is a nice process to get used to setting these things up. Right, this is the embarrassing bit. So, what went wrong, and why did it give these really bizarre values? I was going through this the other day. Right, let's just go back. Let's go through this the other day going, oh yeah, look at these notes, really pleased. And I noticed a big typo. So let's scroll up. I said alloy steel, if you remember. Scroll up, scroll up, scroll up, scroll up, scroll up. Look at that. The size of this wheel. Look at the comparison between the wheels. Right, so these wheels, when you look at the actual dimensions, these wheels are the same wheels. It's the same dimension, roughly the dimension, but look how far they're out. So when I was putting these notes together, I was going through SolidWorks, I was using the Mass Properties tool, and I forgot to assign alloy steel. So that's where this problem came from. I do intend to fix that, but what I meant by is it doesn't affect the learning is purely because the calculation process that we've gone through, the testing of different signals, the setting up of these different signals, the verification based on the incorrect properties for it, still ties in. So what I mean is it's simply a value. The math's good, everything stands, but apart from that. So I do need to still fix that. Right, so if you've not done already, make sure you hit save on that. There's a few little extra nest eggs in there that I put in there just that you might not have seen them before, like using different signal processors, using different damping coefficient. If you've not done, save it, and if you have found a real benefit of that, I hope you did. I hope you found a real benefit behind it. Sorry, I lost my way of thought then. What we will be doing in the next few weeks is we'll be examining on this further. We will look at free body systems that are flowing, be contact mechanics between ball and a flat surface. We'll be looking at linkages, the way that linkages behave and how we can configure. We will do a live configuration setup, so we're probably going to do a double pendulum live configuration. So I'm going to bring in an actual physical double pendulum. We're going to attempt to make it. We're going to have to try and figure out what materials we use, and yeah, let's have some fun. So if I can't think of anything else I haven't shown you, but I'll speak to you soon.